Hello, in this video I'm going to be talking about how to incorporate the AISC shapes database directly into your OpenSees analysis. So here I am on the AISC website and I searched for the shapes database, and you'll see the AISC shapes database version 15 XLSX file right here. If you download this, then it'll bring this up. So you'll have the README here for the database. Describes all the different properties in the database, and then you have the full Excel sheet right here. So this has W sections or wide flange sections. It has everything in it. I mean, C channels, L sections, wide T sections, double L's. I mean, there's like 2,000 entries here. So if you have any sort of steel shape, you can access the values directly here. So one of the issues, though, is that this isn't very conducive to incorporate directly into OpenSees unless you're going to copy and paste the values. First of all, I mean, it's an Excel sheet, and there's not really a direct API for or application interface for Excel and OpenSees. And then additionally, it also includes the SI in the same row, which makes it difficult because these properties are listed twice. So it's not really a true database because there's duplicate fields. So what I've done is I created a little macro here. I have my shape splitter. It's just a little Excel VBA macro that runs if you have the AISC shapes database in the same open in the same instance. And all it does is it just copies over the corresponding columns into separate US and SI unit sheets. And it also does a little bit of pre-processing. It replaces all of these long dashes in the blank columns with just blanks. And then additionally, there's one header that has a Greek letter in it. So just to keep it with all very simple ASCII characters, it's now tangent of A instead of tangent alpha. And that's about it, what it does. So it's already been run, so I have the macro here so you can see exactly what happens and how it runs, and you can try it for yourself. But then it exports these corresponding US and SI sheets into CSV. So here's the shapes-us.csv file. This is in raw text format, so you can see all the data is there. It's just in text format. And I forgot to mention one other thing. Anything that showed up as a fraction in the main database, for example, right here, 5.5 is going to show up in decimal format, so that you don't have to deal with fractions in a programming language. So CSV, it's a pretty simple format. You have rows that are separated by new lines, and the values of the different columns are separated by commas. In the case of the AISC database, there are no spaces or commas or anything in each field name and each value. So it's actually a very, very simple CSV. You can parse it with a very, very, very simple parser. So that's what I've provided. I provided a read AISC procedure in OpenSees. Do not expect this to parse other CSV files unless if they are also very simple. But this does parse a very simple CSV file. So all it does is it takes a file name and it reads it and then splits the lines, and then it actually puts it into a double nested dictionary. Now, a dictionary in Tcl is similar to like a dictionary in Python or other languages as well. It's a way to access values with a key that's not just a integer index. It can be anything. So I have some examples here. So right here, you'd source the procedure wherever it is, and then you can save the AISC database into a variable. So here I'm reading the shapes.-us CSV file, and then I can access it by just doing like dict get AISC and then the shape name and then the property. So it's always you use the dictionary command, and the first field is going to be the shape name, and then the second one is going to be the property name. And with dictionaries, you can do a bunch of different things. Like you can filter, so you can filter the AISC database based to only have wide flange shapes. You could find certain properties that have, or certain shapes that have properties greater than a certain value. You can also use other features of Tcl to get like a list corresponding to like a list of property values corresponding to a list of shapes. If you had like a list of shapes for the different beams of your building or the different columns, then you could get a corresponding list for the like areas or the beam depth, whatever you want to do. So I'm just going to run this really quick. So as you can see, it accessed the shapes database, and I'm able to query shape properties, such as the area of this wide flange section. I can filter the shapes database to have only wide flange shapes. I can filter based off of a property value. So there's lots of things you can do with it. And just a quick side note, this is the US database, and this is in units of inches for the property values. And then for SI, it's mostly in millimeters, but there are some units that are like in mega millimeter to the fourth or something like that. So just consult the AISC shapes database README documentation. There's all the property values are listed there in their units. So this is that. This is very basic access, and so I'm going to show you how you can use it in your model. So here I have a very simple cantilever column model, and I source the read AISC procedure, and I load in the CSV file. And then here I can get the property values directly from the dictionary. So I want to have the moment of inertia be IX, which would be the strong axis bending. And so you can access all the values there. So here I'm doing the same thing for the fiber section properties. So I have the depth of the wide flange section, the flange thickness, the the web thickness, the flange width, and the flange thickness. So here I'm actually using a wide flange section 2D section in OpenSees. This is a kind of a it is a fiber section, but it builds the fibers for you, so you don't have to define each fiber. This only works for 2D strong axis bending. So if you're doing 3D modeling, or if you're doing like weak axis bending, or anything other than a wide flange, you're going to have to define the fiber section yourself. So yeah, but just for this example, I just picked something simple. So here it's a very simple model. It's just 2 nodes, and it's just a cantilever column going out to the side, and I am comparing the model displacement to the theoretical displacement. So this is just an example model that you can kind of play with and try out different loads and see how a nonlinear fiber section behaves in OpenSees versus just the elastic theory. So if I run this really quick, so you'll see in general a fiber section in OpenSees is going to have a larger in magnitude deflection. This is because the fiber section is going to miss out on those little fillet corners on the wide flange section, so right where the web meets the flange. So it misses out on that small little bit of section. So because it's only considering just the rectangular web and the rectangular flange. So that is available on my GitHub here. I have the AISC CSV. So it has the read AISC Tcl file, and it also has the 2 examples that I went over here. And then it also has the version 15 AISC database, and it has the 2 CSV files here. And if you want to regenerate those you can use the Excel macro file. Yeah, so I have a version released here, so you can just download the files right here just by clicking the source code zip, unzip it, and then you can just move the files wherever you need them. And that's about it. I hope this is useful and helpful to anyone who's watching. And if you have any issues with it, any questions, please drop a comment. And as always, have a great day.